Hello friends, in continuation of my last session on queuing theory, today we will discuss the first queuing discipline, that is MM1. Just to summarize what we discussed in the last session, I told you that we must know 5 things to understand a queuing system. The first is the input, and that we consider as the random arrival. Second is input service. It can be finite source or it can be infinite. That is queue length. Then third is the discipline, and I told you 2 discipline. One is first come first served or last in first out, either FIFO or LIFO. But there are other disciplines also, like priority disciplines or random service. Then number of channels, it can be 1 or more than 1. If it is more than 1, it can be in parallel or it can be series. And the 5th one is the distribution of service time. Distribution of service time is also considered to be random, and therefore we consider exponential distribution of service time. Arrival is denoted by lambda and departure by mu, and I told you that lambda upon mu is the utilization rate, and that is denoted by rho. Then I also discussed about the bulking, reneging and joking. But if you ignore these 3, then the queue system which we are going to discuss today is MM1, infinite. Now this is basically indication of random input, random arrival. So it will follow the Poisson distribution. This is random service time. Random service time means it will follow exponential distribution. 1 is the number of channel. Infinite is the queue length, and this is the infinite source. So when you say arrival of vehicles, means source of arrival is infinite, and queue length has the infinite capacity. That is the meaning of these 2, infinite. When I say random, now random basically means the system does not have any memory. So arrival of one vehicle does not depend upon the arrival of previous vehicle. And similarly, randomness in the service time, system does not understand or does not remember how the previous vehicle was serviced. So every time it takes the vehicle or the item as a new item. That is the meaning of randomness. Now, this is the input to a service, and then this is the output. This is mu and this is lambda, and this is 1 channel. That is how you describe MM1. Now here, what is the parameter of interest? The parameters of interest are, what is the probability that there will be n number of vehicles in the system at a given point of time. N can be 0, 1, 2, 3 or any number. What is the length of the queue? What is the number of items in the system? How much is the average waiting time in the system? And how much is the average waiting time in the queue? Now when we say the average time in the queue or average length of the queue, it does not consider the items which are already being served. That means the vehicle which is in the channel, that is not considered. There is a difference between the number in the queue and number in the system. A queuing system is said to be in the state of n if it contains exactly n items in the system. Now this n includes the item which is being served or which is in the channel. And let us say Pn is the probability of having n number of items in time t plus delta t. That is the probability of having n item in the queue system, n vehicles in the queue system. Now this can be achieved by three methods, or you can say that there are three possibilities of having Pn or n number in the system at time t is equal to t plus delta t. Delta t is very small, and the basic requirement of delta t is that only one event can occur in delta t. So it will be either arrival or it can be a departure. Not simultaneous arrival and departure, not parallel arrival. It can be that there were n plus 1 vehicle at time t and one vehicle departed during delta t. One vehicle departed, or one departure you can say, plus no arrival. Delta t is very small. Or it can be that there were n minus 1 vehicles, n minus 1 items in the system at time t and one arrival. One vehicle arrived during delta t and no departure. No departure. Or it can be like there were n items in the system at time t and during delta t no arrival and no departure. Now these are three mutually exclusive events, and therefore probability will be sum of these three probabilities. Now what is the probability that there will be one arrival in delta time t? And I told you this arrival is random. It follows Poisson distribution, and if you remember, the equation of Poisson distribution is that, so probability of being x vehicle arriving in time t is given by this equation E minus lambda into lambda power x upon factorial x. Lambda is the average rate of arrival. Now if you take delta t as the time interval, it will be time interval, and here it will be x. So this will be the probability of, you can say, x arrivals in delta time t. And if you take x equal to 1, then this probability of one arrival will be e to the power minus delta. Delta is the rate of arrival into delta t into delta t into lambda divided by 1. This is lambda into delta t, and this is exponential series. You can open it. That is delta t plus delta t by factorial 2 plus and so on, infinite series. Now because I told you delta t is very small, and therefore if you ignore the higher order terms of delta t, then it will be lambda into delta t. This is the probability of one arrival, lambda into delta t. If you take the probability of no arrival or 0, then it will be by the same, it will be 1 minus lambda into delta t, p0. Similarly, the probability of one departure will be mu into delta t, and probability of no departure during time delta t will be 1 minus mu into delta t. So come back to this. Probability of n vehicles in the system at time t plus delta t is probability of n plus 1 into one vehicle departed, that is mu into delta t, no vehicle arrived, delta t, plus probability of n minus 1 into one arrival, that is lambda into delta t multiplied by 1 minus mu into delta t, and no arrival, no departure, plus probability of n into 1 minus lambda delta t 1 minus mu delta t. That is the probability that the system will be in the state n. There will be n items in the system. Now, if you simplify this equation and again ignore the higher order terms of delta t, mu delta t multiplied by delta lambda into delta t, that will be delta t square. If you ignore all those terms, then this equation will be Pn t plus delta t minus Pn t divided by delta t equal to Pn minus 1 t into lambda plus Pn plus 1 at time t into mu minus Pn lambda plus mu. This will be the equation. Now delta t is very small. This is the differentiation or derivative of probability. So if delta t, limit delta t tends to be 0, then this becomes the dp upon dt. Now for a steady state, now when I say the Q will be in the steady state or system will be in a steady state, it means it is stabilized over a very long period of time. So this becomes 0. Differentiation of or derivative of probability becomes 0. So if you put this equal to 0 and then simplify this, you get lambda Pn minus 1 plus mu into Pn plus 1 equal to lambda plus mu into Pn. Let us say equation number 1. Now let us make a small change here. Instead of taking n vehicles in the system, let us say there is no vehicle in the system. N is 0. So in that case, when n is 0, what is the probability P0? Now there can be two ways when probability of having 0 items in the system. The one is that probability of having one item at t is equal to t plus one departure during time delta t and no arrival, or it can be P0 at time t and no arrival and no departure. No departure during time delta t. Now third option or third possibility will not apply here because it cannot be minus 1. Now P1t into one departure, that is mu into delta t, no arrival 1 minus lambda into delta t. That is the probability. P0 plus P0t, no arrival 1 minus lambda into delta t. What is the probability of no departure when there is no vehicle in the system? The probability of no departure, because there is no vehicle, so it will be 1. Probability of being no vehicle in the system at time t plus delta t will be P1 into T multiplied by U into delta T into 1 minus lambda delta T plus P naught at time T into 1 minus lambda delta T into 1. Again, if you ignore high order terms of delta T, simplify this equation, it will be written like this: P0 T plus delta T minus P0 T upon delta T is equal to P1 at time T into mu minus P0 T into lambda. And by the same logic, if this derivative is taken equal to 0, then this becomes equal to 0. Now, this gives you P1 because T is now removed. So, mu into P1 is lambda into P0, or P1 is lambda upon mu into. Now, this is utilization rate, rho. This is equal to rho into P naught. This is equation number 2. Now, if you put here in this equation n is equal to 1, 2, 3, 4, 5, you can find out what would be the probability in terms of P0. So, let us say n is 1. N is 1 in equation 1. So, this is lambda into P0 plus mu into P2 is lambda plus mu into P1. Put the value of P1 equal to rho into P0 and simplify. You will see that this P2 is rho square into P0. And similarly, if you keep on doing it, probability of having n vehicles is rho power n into P0. Now, what is P0 here? Now, P0 here can be found out by putting the sum of all probabilities equal to 1. That is P0 plus P1 plus P2 plus and so on infinity equal to 1. P0 plus P1 is rho P0 plus rho square P0 plus and so on rho power n into P0 plus up to infinity equal to 1. Now, this is P0 1 plus rho square plus rho cube and so on up to infinity equal to 1. This infinite series with rho equal to less than 1, that is the requirement of a steady state, and therefore its sum will be, that is P0 into 1 upon 1 minus rho equal to 1, and therefore P0 is 1 minus rho. P0 is 1 minus rho, and therefore this Pn will be equal to 1 minus rho into rho power n. That is the probability of having n number of vehicles in the system. Means Q is in state n. Now, once you know the probability, the next interest is to find out what is the expected number. So, mean of this distribution is, that is your expected number, or you can say length of the system, length of the vehicles in the system, LS is equal to rho upon 1 minus rho. This is the expected number of the items or the vehicles in the system. Length of Q will not be exactly LS minus 1 because there is a definite probability that there will be no vehicle or no item in the system, P0. And therefore, this length of Q, LQ, will be Ls minus rho. That is utilization rate, lambda upon mu. Now, waiting time in the queue and waiting time in the system, they can be determined by very popular Little's rule. And what Little rule says, that Ls is equal to lambda time Ws and Lq is lambda times Wq. Now, this is the waiting time in the system, waiting time in the queue. Lambda rate of arrival, Ls we have calculated here. Now, Ls is rho upon 1 minus rho, and if you put this rho upon 1 minus rho here, it will be rho square upon 1 minus rho. So, waiting time in the system, Ls will be 1 upon lambda into rho upon 1 minus rho. Again, simplify this, it will be 1 upon mu into 1 minus rho. This is waiting time in the system. And similarly, waiting time in the queue will be 1 upon lambda into LQ. LQ is rho square upon 1 minus rho, and this is equal to rho upon mu into 1 minus rho. So these are the parameters of interest. What is the expected number of vehicles in the system or in the queue? What is the probability of having n number in the system, and what are the waiting times? Now let me very quickly take one example. Suppose you have a toll booth. Rate of arrival is 500 vehicles per hour and rate of departure is 700 vehicles per hour. There is one service channel. What is the probability or what is the percent time the operator will be free? Operator will be free. That is P0. What is the probability of having no vehicle in the system? P0 is 1 minus rho. What is rho? Rho is 500 upon 700. 5 by 7. That is 0.714, and therefore probability of having no vehicle is 0.286. 28.6% time the operator will be free. There will be no vehicle in the system. Now next is average queue. Average queue size in the system. Average queue size in the system, Ls. Ls is given by rho upon 1 minus rho, and rho you know 0.714 divided by 0.286, that is 2.5. 2.5. And what is the queue size without system? What is the length of the queue when you do not consider the item in the system? That is Ls minus rho. So 2.5 minus 0.714, that is 1.78. 1.78 vehicles in the queue on an average, 2.5 vehicles in the system. And similarly, you can find out what is the waiting time. Average waiting time in the system, Ws, is 1 upon mu into 1 minus rho, and if you put value of mu 700, 1 minus rho, that is 0.286, you get, and multiply this by 3600 to get in seconds, you get 12.86 seconds. So that is how this MM1 model or queuing discipline is solved. Thank you very much for watching this video. In the next session, we will discuss when you have the finite number of queue length.